Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be looking at lattice energies. This is more or less just a way to talk about how stable an ionic system is. So one of the big things is remember that ionic solids, what really makes them so favorable is that attractive nature of the positive and negative charges. And we can go ahead and evaluate how easily these charges come together by using what's called the lattice energy. And this is more or less the energy that would be produced, so this will be a negative number, if I took the cations and the anions in the gas phase where they experience absolutely no intermolecular forces, I mix them together and we'd expect them to, again, assemble into our solid salt form, which would be the most stable nature. So for example, if I'm going to go ahead and look at lithium fluoride, so a relatively one-to-one salt, I'd be taking lithium cations and fluoride anions, both in the gas phase, let them deposit into a solid salt lattice. And again, this should be the lattice enthalpy, and it should be quite negative or quite exothermic. Unfortunately, it turns out you can't actually really perform this experiment because it's very hard to get ions into the gas phase, and definitely to do so while they aren't interacting. So what we need to do is find another value that will help us look at the energy of this lattice, or this salt. Unfortunately, all we really have is enthalpies of formation. Now, this does have the right product, which is very good. But if we take a look at the reactants, we run into some slight problems because if we look at this, for example, lithium is in the wrong phase, and both lithium and fluoride have the wrong charges. Lithium, we want to be positive, and again, in the gas phase, and fluoride, we need to split that apart and give it a negative charge. So we're only like halfway-ish there. So what we can do is make use of Hess's law. And this is a specific form of Hess's law called a Born-Haber cycle. So what you do in a Born-Haber cycle is you go ahead and combine together a whole bunch of elementary reactions into a cyclic pattern where you end up generating the right product. So the major idea is that we have two different ways to generate the same thing. So I could either take lithium and fluoride gas, combine it together to make the solid, or I could go ahead and take that lithium solid, turn it into a lithium ion gas, split apart my fluoride and ionize it, then recombine them to make the using the lattice reaction to generate the solid. Both of these patterns should be the same. So again, going from solid to gas, doing this, we have to first sublimate, and then we need to ionize. However, we can usually look up the sublimation enthalpy and the ionization energy pretty easily. Then we have to find the bond dissociation energy, which is usually readily available for diatomics, and the electron affinity, which again, we saw was quite easy to find last semester. So then when you combine these, you get the right reactants. But we now need to go ahead and account for the generation of the products using the formation reaction. So you can go ahead and do this by saying that the formation reaction, again, going from our elemental species to the product, would be the same thing as adding together the sublimation reaction, the first ionization energy of lithium, the dissociation energy of fluoride, the activation energy of electron affinity of fluoride, and the lattice enthalpy. Then we can look up all of these energies except for the lattice energy in a table, and thus solve for the last one. So this is one way of looking at how these Born-Haber cycles or lattice enthalpies work. However, we can also kind of describe this a little bit more pictorially and a little bit more as a cycle. So again, we're going to take these same 5 reaction steps, and really what we're going to be looking at is 2 different ways to get to the same place. If we're going up in energy, that will be depicted as going up. If it's going down in energy, we'll be lowering. So our lattice enthalpy would be the reverse of this last reaction, going from the ions to the solid. So what we can do is just find the 2 different ways to getting there. So we can go ahead and start with looking at our first step is going to be sublimating that sodium solid, so solid to gas. Then second step is ionizing that sodium to make a positive cation in the gas phase. Next step is going to be taking that chlorine, disassociating it, and once it's in the gas phase, then we can apply the electron affinity. Again, this will produce energy to generate a negative ion. Then we have to account for the enthalpy of formation. Note that this will be a negative value here because normally enthalpy of formation will again be a positive number, will be a negative number as I'd be going from the ions to here. However, we're looking for the reverse reaction. So going from sodium chloride to the elemental species. So that should be positive, increase in energy. So we'll tag a negative sign on. So summing up all these 5 steps would be the enthalpy for the generation of the sodium chloride. And again, if we're looking for the lattice energy, you simply take the negative of this. So when working with lattice energies, do make sure to take special caution if you're calculating the lattice energy of anything that isn't a simple one-to-one solid like we just saw. So if we're working with anything like magnesium chloride, there's going to be lots of little differences. So for example, you won't have a single ionization energy, you'll have multiple ionization energies. And you won't be producing 1 chloride ion, you'll be producing 2 chloride ions. But otherwise, as long as you're remembering to account for stoichiometry, you should be fine. However, using these sorts of different lattice energies, we can end up indicating several cool features. First of all, higher lattice energies will indicate that a solid is more stable. We'll get more energy for interactions. And in generally, one of the things we're going to find is as the ions tend to get higher charges, it may be harder to form those ions, but if they form naturally, something like calcium 2+, they tend to produce much more stable solids because there is more Coulomb interactions to occur. There's more positive to reach out to neighboring negatives, and that is worth acknowledging. So next time, we're going to go ahead and try and encapsulate some of the big take-home lessons from this admittedly slightly long chapter. Until then, take care.